Hey everybody, this is Mr. Murray and Mr. Murray's Mathland, and today we're taking a look at Riemann sums, specifically left and right types of Riemann sums, left and right rectangles, to approximate the area under a curve, between the curve and the x-axis specifically. So we're taking a look at a nice simple function here, one you should be familiar with. The f of x equals e to the x is exponential growth. And we're trying to estimate the area underneath the curve between x equals 1 and x equals 3, over that interval 1 to 3, using a Riemann sum with equally spaced subintervals and 4 left rectangles, and then I'm going to do it with 4 right rectangles so you can see the difference and the similarities between the two approaches. So first of all, visualizing what is going on here. Here is the region we're talking about, between 1 and 3, and the area underneath there talking about finding the area of that. So as you can see, it's not a simple, geometric figure. It's got that curve on it, and it's not a semicircle or anything we can deal with from geometry. It's an exponential curve. So this is where the approximations come into play. So first thing first is to determine how wide each rectangle is going to be. I know how to find the area of a rectangle. It's base times height, but what is that base? What's that height? So we are going over the interval of 1 to 3, and so that's a total distance of 2 units. And we always want to divide that up by how many items we're making, how many rectangles we're making. So we are dividing that up by 4, and it did specify equally spaced. So our delta x, our difference in x, as you're going to see in a moment, is always found by doing the width of the interval, that's 3 minus 1, that gives us 2, divided by how many rectangles you're making. So 2 divided by 4 gives us a nice even width of 1/2 or 0.5. So here's the visualization of that. Going 1 to 3, and every half unit, or every 0.5, so at 1.5, then at 2, then at 2.5, and then at 3, we're sort of breaking this one big region up into 4 smaller sub-intervals, 4 smaller regions. And the more and more I break it up, the more they start to resemble a rectangle, each one roughly. So this first region we're going to do, and sometimes this is abbreviated as L4 to show I'm doing left rectangles and I'm doing 4 of them. Well, the base of this first rectangle here is this region I'm talking about. The base of it is 0.5. That's our delta x. That's where that's going to come into play. So I'm going to write this out kind of a long way the first time, and then we'll see how we can shorten it up. But this first rectangle has a base of 0.5 or 1/2, and the height of it is where the left part comes into play, because as you can see, if I use this side as the height, it's going to be a shorter rectangle. If I use the right side as the height, it's going to be a taller rectangle. And so we're doing left rectangles, so that means for each interval, you're going to use wherever that left side of the interval hits the curve, and you draw straight over, and that is going to be your rectangle. Now, what is that height? That height is f of 1. That would be the y value, plugging 1 into whatever function you're dealing with, or in this case, e to the first, which is e. But I'm not even going to bother writing that, because sometimes the function can be pretty messy, so I'm just going to write f of 1 as shorthand. And then in the next interval here, between 1.5 and 2, again, the base is 0.5. That doesn't change. And the height of that rectangle, I'm going to use the left side of that interval where that hits the curve. So that would be plus another base of 0.5 times the height of f of 1.5. The third rectangle, which would be between 2 and 2.5, I'm going to again use the left side of the interval as the height. So where that hits the curve, so that would be again a base of 0.5 times f of 2, right? That's where we're using this value here. These are the three values we're plugging into the function to get those heights. And for my fourth rectangle, we're using this last region here. We are using 2.5 to plug into the function and get the height. So that would be, again, another 0.5 times f of 2.5. Got a little scrunched in there on the side. And as you can see, you know, the thing that's being used over and over again is that 0.5. So for shorthand in the future, once you get good at these, you do a couple of them, you'll probably just set it up this way in factored form. Hey, if I'm having a delta x of 1/2 or 0.5, I can factor that right out of the whole expression and then just add up all of these heights individually. So 0.5 times f of 1 plus f of, and then you notice how the x value inside that function increases by that same delta x. So if you don't have a graph in front of you, which is nice to visualize, but you don't really need it. If you know I'm starting at 1, then I know each x value is going to increase by 0.5. So f of 2, and finally f of 2.5. And now I'm going to get that value from my calculator, because this is an e to the x kind of graph. And when I go and get this from my calculator, I really don't want to get these values f of 1, f of 1.5, f of 2. I don't want to get them one at a time and then round them off and then add them all up and multiply them by 0.5, because you might be losing a little bit of accuracy. So I mean, you can do those kinds of things if you want to be careful and write out enough decimals you feel comfortable with. But here's another little trick here we've played around with on the calculator before. I'm going to put in y1, I'm going to put the curve I'm dealing with, which is e to the x. So that would be the second ln button and then x. And now I've got that stored in y1. I'm going to go back to the home screen. So quit, second mode here to get back there. And then I'm going to type in one big expression, 0.5 parentheses, and now instead of f on our calculator we use y1. So that would be the alpha trace, the F4 menu, or you go to vars and yvars if you don't have those shortcut menus. So y1 of 1, that's the same thing as f of 1, plus y1, just bringing it back. And this might seem like it's kind of time consuming, but it's a lot faster than getting the values individually. y1 of 1.5 plus alpha trace y1 of 2, and lastly alpha trace y1 of 2.5. And you still have to be careful that you don't use, you don't leave out any parentheses, and that's always a challenge with calculators, especially you got to scroll back if it's a long enough expression. But I'm confident I typed it in correctly. And so here we go. That is the approximation, is about 13.385 or 386. You can round or truncate. I like to round. And there we go. There's the approximation using 4 left rectangles. Now let's talk about 4 right rectangles and how that is the same and how it's different. You're still making 4 objects, so my delta x is still that same 0.5 or 1/2. The only difference here is which side of the interval you use as the height. So for example, that first interval here, and so now I'm going to be doing right sub 4, so they're going to all have that 0.5 base. So I'm going to go right to my factored version. They're all going to have 0.5, 0.5, 0.5, 0.5. I'm just going to add up all the heights, and the heights are going to come from the function. But that first interval between 1 and 1.5, you're going to use 1.5, the right side of the interval, where that hits the curve. And so you can see that rectangle is actually going to be a little bit over the curve, but that's okay. It's only an approximation. So this would be f of 1.5 plus f of, in the next interval, between 1.5 and 2, you use the right side of that region, which would be f of 2. Again, notice how once you know where you're starting, if I'm starting at 1.5, the x value you're plugging in increases by that delta x. That's the whole point of the delta, right? The difference. And the next interval, you're using 2.5, or f of 2.5, as the height. And lastly, between 2.5 and 3, you're using f of 3 as your height. So similar to the left setup here, when you start with the left, you start with f of 1, 1.5, 2, 2.5, and you leave out 3. You leave out the far right side of the interval. When you do the right, you end up with everything except the far left, 1.5, 2, 2.5, and 3. And so now, as far as getting that approximation here, you can, of course, retype that in your calculator. But if you've already typed part A in for left, and you realize this setup is exactly the same. I'm using f of 1.5, f of 2, f of 2.5. The only difference is instead of f1, I'm using f of 3. I could just take a little shortcut here, bring that whole expression back by hitting, second enter, or you can scroll back and hit enter, bring that whole expression back, and just go and change that f of 1 or y1 of 1 to 3, and save yourself a lot of time here. And you see you get an approximation of 22.069. Whether you round or truncate, everybody should have that exact value. And as you can see, these approximations are kind of far apart, and we talk about that, getting better and better approximations as we go on. But notice how the left one is definitely an underestimate. You can see when we drew those left rectangles, they were under the curve, leaving out that space. And the right was definitely, every rectangle was over the curve, so we're definitely over the real amount. So our actual amount is somewhere between these two. It's not an exact average, but it's somewhere between those two. And the more rectangles I draw, the more that approximation will get tightened up. But we'll talk about those kinds of things in the coming days and other videos. So let me know if you got any questions, and hopefully this made it pretty clear, the visual and the algebraic way to get it.